Problem 217. We are given a force F, which is equal to 40I minus 20J. So, if you look at the left-hand side, this is a vector because it has an arrow on top. And if you look at the right-hand side, since the left-hand side is a vector, right-hand side better be a vector. You have a scalar times a unit vector, that should give you a vector, minus another scalar times another unit vector, that's another vector, and you take a vector, you minus another vector, you end up with a vector. So it's all good. Graphically, if you were going to plot this, 40 in the I direction, if this is your unit vector I of length 1, you take 40 of those, 1, 2, 3, 4, 5, up to 40. I'm not going to do it, but it's somewhere on there. And J is a line along the Y component, but it has a negative sign, therefore you want to go in the opposite direction. So if J has the same length 1 as I, you go minus 20 in the negative direction, and this should be your vector F. So usually a vector in the first quadrant has both x and y positive. A vector in the second quadrant has the x negative and the y positive. A vector in the third quadrant has both components negative. And a vector like we just have in the fourth quadrant has only the y component negative. So they're asking us for the magnitude of f. So since f is equal to 40I minus 20J, fx is 40, fy is minus 20, therefore the magnitude is the square of both. You add them up, you take the square root, you end up with the magnitude. So in this case you have 40. My bad. This should be technically with vectors, because magnitude cannot be negative. So you have 40 squared plus minus 20 squared, you take the square root, and you end up with roughly 44.7 Newton. Let's imagine that you were looking for the unit vector. It's not being asked, but we can practice that. Let's call the unit vector EF. Then you can take your original vector F divided by its magnitude, and you end up with 1 over 44.7 times the vector itself, which was 40I minus 20J.